Okay, so we've basically spoken about this already because we've looked at the number of successful collisions per second, and that is in short just called reaction rate. Now, if the number of successful collisions per second means that I would look at the moles produced or the moles used up every second, which means divided by time. This is the formula for reaction rate. I would look at how many moles were produced within a certain time, and that would give me my reaction rate. Now, if we were to look at a reaction happening, then obviously, so let's say this is the amount of moles that I have, and this is time. Then let's just look at what a typical graph would look like, starting with the graph for the products. Okay, let's start with the products because it's easy. Initially, how much product will I have? I can't hear? Nothing. I don't have any product. Product is what I'm trying to produce. So at time 0, I have no products. Now, when I put my reactants together or my reaction starts, I will very quickly, if after a little while, I will measure how much reactant products I have. And then after a little while, I will measure again how much I have, and then after a little while, I will measure again. But eventually, this will start happening to my products. Notice that it's not a straight line upwards. It doesn't forever just continue to have the same, we call it yield. Okay, that means how much is produced every second. Okay, it would rather have, and if I now connect the dots, a shape like this. Could you explain to me why? If we look at the gradient of this graph now, the gradient represents the reaction rate. Because remember what we said, moles produced is the change in mole divided by a change in time. That's a change in y over a change in x. So that's gradient. So the gradient of this graph represents the reaction rate. The steeper the gradient, this more is. If it's a positive, it means it's producing. And if we now look at our reactants, let's say we have 2 reactants. With one reactant, I start here, and over time, it is used up. So my moles is becoming less and less and less until at some point I reach this horizontal state. Another reactant, that one in red, another reactant also, when I measure it, it is doing that. And this one of the reactants have to go to 0. Okay, unless it's a reverse reaction. If it's a reverse reaction, it will be a little bit different. So let's for now assume it's not a reverse reaction, which means one of my products gets used up. That's what this means. That's why this one goes all the way to the floor. It gets used up. Now, can you tell me why is the reaction rate? Now, remember what we said the reaction rate is. It's the number of successful collisions every second. Why is that decreasing over time?
Could it be because reactants get used up?
No. There's fewer molecules to actually... So they still have the same amount of kinetic energy. Okay? But now there's fewer of them around because some of them have collided and formed products. So there's fewer. And as there's fewer and fewer, there's fewer actual reactants that can collide to form successful collisions. Okay? And at some point, there's no more of one of the reactants. There might be another one left. And so at this point, where there's no more of the one, this is now in a non-reversible reaction. In other words, one of the reactants was used up, and the products don't produce reactants again, and that would be non-reversible. Then that is why there is no change in the amount of products formed anymore. This is the amount of product formed, and that's it. It doesn't increase after that. Can't. Okay, one of my ingredients is finished. Can't make more if I don't have more ingredients. Does that make sense? Okay. So that is why you will notice that in a reaction rate graph, you will always have, or you should always have, that your action rate decreases over time. And it does make sense why. Doesn't it? Okay. You are nodding too slow. You should nod like those cartoon characters. Okay.